Have you ever wondered why roots of polynomials with real coefficients always occur in conjugate pairs? Well, if you've probably not noticed this, let's start with the roots of a quadratic equation. Let's say that you have a quadratic equation, x squared minus 2x plus 5 is equal to 0. What are the roots of this quadratic equation? Well, you know that the two roots are minus b plus square root of b squared minus 4ac over 2a and minus b minus square root of b squared minus 4ac over 2a, right? And you notice that they are complex conjugates. So for example, in this case, it's 2 plus square root of 4 minus 20 over 2, and the second root is 2 minus square root of 4 minus 20 over 2. So clearly this is 1 plus j2 and this is 1 minus 2j. So they are complex conjugates of each other, right? And you will see that this is true for any quadratic equation which has real coefficients. And it turns out this is true in more generality, in the sense if you have, let's say you have a cubic equation instead of a, so for example, let's say you have a equation which is x cubed minus 4x squared plus 6x minus 4 is equal to 0. And if you compute the roots of this equation, it turns out that the roots are 2, 1 plus j, and 1 minus j. And you can see that these two roots occur as conjugate pairs. And what I'm going to show in this video is that for any polynomial, not just a quadratic or a cubic, as long as the coefficients in the polynomial are real, roots will always have to occur in complex conjugate pairs. Okay, so here is the proof of this curious fact. So let's say we have a polynomial, and I'm going to call the polynomial as x to the n plus a n minus 1 x to the n minus 1 plus so on and so forth until a1x plus a naught. And let's say that the equation is that this polynomial is equal to 0. Now if this polynomial is equal to 0, then what must be true is that we should be able to factor this polynomial into its roots, right? So let's say that this polynomial, we'll call this as p of x. But we know that p of x factors into the product of its roots. So we can write this polynomial as x minus r1 times x minus r2, so on and so forth until x minus rn. So what we're going to do is we're going to conjugate both sides. So let's take the complex conjugate on the left side and on the right side. So what do I get when I take the complex conjugate on the left side? What we are going to get is conjugate of x raised to n plus the conjugate of a n minus 1 times x conjugate raised to n minus 1 plus the conjugate of a1 times conjugate of x plus the conjugate of a naught on the left hand side. On the right hand side, we're going to get x conjugate minus r1 conjugate, x conjugate minus r2 conjugate, so on and so forth until x conjugate minus rn conjugate. Now what we know is that these a's are real. We don't know anything about these roots, r1 through rn's, but we know that the a's are real. So what does it mean to take the conjugate of something that's real? So if I take the conjugate of a real number, I need to get the same real number again. So the conjugate of a, all these coefficients is the same as the coefficients themselves, so I can remove the conjugate from these coefficients. Okay. Now, I'm just going to call x conjugate as y. And now you will notice that you get yn plus an minus 1 times yn minus 1 plus so on and so forth until a1 times y plus a naught is equal to y minus r1 conjugate times y minus r2 conjugate, so on and so forth until y minus rn conjugate. Okay. Now notice that y is just an indeterminate, right? X and y's, they are just variables. So if I look at these two equations, you can see that these two equations are exactly the same. So I could just replace y with x and I would have exactly the same equation here. And what that tells me is that, or maybe we'll just do it and we'll see some. So let's say this means so notice that these two equations are exactly the same. The first and last equations are exactly the same. But on the right hand side, the roots of these equations are r1 through rn, whereas the roots of this equation are r1 conjugate through rn conjugate. So that tells you if r1 is a root of this equation, r1 conjugate is also a root of this equation. In other words, roots occur in complex conjugate pairs. Of course, these conjugates are not new roots. So what this just tells you is one of these other roots here must have been the conjugate of r1. And one of these other roots here is the conjugate of r2, so on and so forth. Now, this itself is not something that you might really see a lot as an undergraduate in electrical engineering. It is just a curious fact. And if you ever study finite fields, later on, it might help you understand conjugates in finite fields a bit easier.